Section 4.6, CPCTC and substitution property. So we're going to use triangle congruence theorems that we've been learning to prove that two angles or two sides are congruent in that weren't given. So you know that you can use the following postulates or theorems to prove that two triangles are congruent. So we know we can use these. But what does it really mean? Once we've proven those two triangles are congruent, then what it means is that every side is congruent to its corresponding side on that other triangle, and every angle is congruent to its corresponding angle on that other triangle. So once we prove two triangles are congruent, remember every corresponding side and every corresponding angle will also be congruent. So, for example, we know that these two triangles are congruent. How? Side, side, side. So because that, we know that angle B right here will be congruent to angle E. How do we know that? Because it's the angle that is marked between the 2 and 3 tick marked angles. So that would be angle E. We know that angle D right here is corresponding and congruent to the one that's between the 1 and 3 tick mark angles. So that would be congruent to angle A. And angle C right here is corresponding and congruent to angle F. So it does make a difference which sides it's between, included between. And we already know the sides are already marked, but we know that ED right here is corresponding and congruent to the other 3 tick mark side of BA. And we know AC is 1 tick mark, and so that is corresponding and congruent to DF. Notice that I'm naming AC from the 2 over to the 3 tick mark angle, so I do the same thing over here, DF. Even though it's the same segment, that's the more common way and appropriate way to name it. And last but not least, we have BC going from the 1 to the 3. Then on the other triangle would go from the 1 to the 3 tick mark angle of EF. So there's a lot of little picky details in here. So corresponding parts of congruent triangles are congruent, and that's what CPCTC stands for. That corresponding parts of congruent triangles are congruent. CPCTC. So again, if two triangles are congruent, then every corresponding side and angle are also congruent. So, explain how you would prove that angle D is congruent to angle H. Well, angle D would be congruent to angle H. Really, we could just say by the third angles theorem. But sometimes you don't remember those. So let's see if we can do it using proving the two triangles are congruent. Could we prove these two triangles are congruent? Well, what we have is we have angle, side, angle. We have angle, side, angle. So is angle, side, angle one of our congruence postulates? Angle, side, angle, yes. So how I would explain how I would do this is I would show that angle E is congruent to angle G. And I would show that angle S, or the side that's congruent, would be ED is congruent to GH. And then I could also show that angle C is congruent to angle F. So what I've shown now is angle right here, the side, and then the angle. So once I have that, so now I know that triangle EDC is congruent to triangle GHF by angle, side, angle. So then that implies that angle D is congruent to angle H, which is what we were supposed to prove by using CPCTC. And that is kind of how we start to learn how to prove things, is we go through sort of a process of explaining, and we try to make it a process. We could do a paragraph and explain it in a paragraph. Right now, I'm just kind of explaining it through the process of listing the angles and sides that are congruent, that would prove the triangles are congruent. Okay, so let's explain how we would prove. What we are trying to prove here is we are trying to prove that TR is congruent to LN. We don't have that marked, and we can't just say they're congruent because they look congruent. But what we can do is try to prove the two triangles are congruent. So can we do that? Well, let's see what we have. We have this angle right here and this angle right here are corresponding and congruent. So we have an angle in each. We have another angle in each, this right angle. So we have another angle in each. And then we have this side right here in each. So we have a side. So what we have is we have angle, angle, side. Angle, angle, side. So yes, we do have a congruence theorem or postulate with angle, angle, side. So how I would prove that these two triangles are congruent is using angle, angle, side. And so I would list, and I'm not going to list the right angle first because then that's in the wrong order. So I have to list the first angle that I'm showing, which would be that angle L is congruent to angle T. Then I would do the right angle, that angle S is congruent to angle M. And finally, I would do the side. I would do the side SR is congruent to the side MN. So triangle STR then is congruent to triangle MLN using angle, angle, side. And therefore, it implies then, now we know, because corresponding parts of congruent triangles are congruent, now we can say that TR is congruent to LN. Again, that's what we needed to prove, but we needed to prove the triangles were congruent first. And then, once we have the triangles are congruent, then we use CPCTC, because corresponding parts of congruent triangles are congruent. Let's look at the substitution property. So the substitution property of equality says if A equals B, then A can be substituted for B in any equation or expression. So in algebra, this property would be used if you have like a system of equations, and you would substitute what y is equal to in for y. And that would give you 2x plus 5 times 4x equals 44. And then we could go ahead and solve that and find the value of x. And then we could now substitute the value of x back in to find the y value. That's what we do in algebra. So how is this used in geometry? In geometry, there are multiple uses for this property. For example, in triangle ABC and DCB, they're both isosceles triangles with bases AC and BD respectively. So if we have AC is the base of an isosceles triangle, then that means these legs are congruent to each other. And in this triangle, if we have DB is an isosceles base, then these are congruent. Those are the legs that are congruent. So then AB is congruent to BC, because that's by definition of isosceles triangle, you need two congruent sides. The other is called the base. We're going to actually talk about that a little bit more tomorrow. And DC is congruent to BC, again by definition of isosceles. So therefore, what we can say is we can actually say that AB is congruent to DC, because what we can do is, since these, we can substitute what BC is equal to right here in for BC in the first expression. So we take out what BC is and put in what segment it's equal to. And that's kind of the transitive property that we talked about as well. Or here's another example. Maybe this one will resonate a little bit more with you. Another example is in the exterior angles theorem. So we know that angle 3 plus angle 1 plus angle 2 equals 180 degrees. We know that because of triangle sum. We also know that angle 3 and angle 4 equals 180 degrees because that is a linear pair. This is triangle sum. So what we can conclude then is we can substitute what 180 degrees, these are both 180 degrees. We can substitute what 180 degrees is equal to in for 180. So then what we would have here, if I wrote it out, is we would have angle 3 plus angle 2 plus angle 1 is equal to 180, but we're going to take that out and put in angle 3 plus angle 4. So now if I subtract angle 3 from each side, what I get is that angle 2 plus angle 1 is equal to angle 4. And that is the exterior angles theorem. So that's how we use substitution. I'm going to go through one little example, like an application problem where using congruent triangles for measurement is very useful. So it says, use the following method to find the distance across a river from point N to point P. So if we want to know the distance across this river, we can't just like take a tape measure and swim across. I mean, sometimes it's just not realistic to do. But what we can do is we can place a stake at point K right here. And then what we can do is make sure that this segment right here, NK, that's not a very great color, I'll use this. We can use this segment, we can make sure that it is perpendicular to NP. So we can make sure that it's perpendicular right there. And then what we can do is we can find the midpoint. So that's easy enough to do because we're on the same side of the river. So we can find the midpoint, which makes those two pieces congruent. And then what we can do is locate this point L right here. So this point L right down here, so that this segment right here now is perpendicular to NK as well. So we can make sure that this segment, we can locate that point so that it's perpendicular. So now what we have is we can actually prove that these segments are congruent right here and right here because we have vertical angles right here. And so what we have is the triangles are congruent with angle side angle. So our triangles are congruent by the vertical angles, the side that we did the midpoint, and then the other angle, which is the perpendicular 90 degree. And once we prove those triangles are congruent, then all we have to do is measure this side right here because it will be the same as this. And this is a lot of the things that they do in surveying. This is actually in your textbook. You can always look back and see, but the solution is listed there. So kind of an interesting way to apply what we've been doing with our triangle congruence and then applying CPCTC so that we can actually measure things that are very difficult to measure. That is the end of section 4.6.